Since every physical quantity must have the dimension, when we express our calculation results, we have to be careful about the dimension also. The number in physics is not just a number. It has a dimension, and you have to be careful on this dimension. When you write down mathematically 1 equal to 1, that's all. But when you write down the dimension, when you write down the physical quantity 1 equal to 1, it means that the dimension on the left and on the right of the equation must agree. So this is what we have to be careful. Put it in another way, we can use this to check our results. If we do any calculation and we found that the dimension on both sides agree, it's likely that our calculation is correct. The next step that you have to check numerically or the algebraic expression of your result, are they correct or not? But if you found that the dimension on both sides are not agree, it's certainly that your result is incorrect, and you have to find out where it's wrong in your calculation. Okay, this is the topic of the dimensional analysis. It means that you can analyze your results. You can analyze the dimension of your results to check that if it's correct or not, and it helps. Sometimes it helps much because you don't have to go into the detail of the number or in the detail of the algebraic expression. You just check the dimension, and if you found that on both sides the dimension are not agree, something wrong. Okay. We have three important conditions for the dimension. That is, first, you can multiply or divide two quantity. Two quantity, those have different dimension. You can multiply or divide it two quantity. Those have different dimension. The example is as in the previous table. When you want to specify the dimension of the speed, it is the dimension of the length divided by the dimension of time. If you want to specify the dimension of area, it is the dimension of the length times the dimension of the length. So you can multiply or divide two quantities that have the different dimension. Okay. The area may not so clear. Later you may want to specify the dimension. For example, the work. It is the force times the distance. So the dimension of the work is the dimension of the force times the dimension of the distance. So you can multiply the quantity that have different dimensions. But you cannot add or subtract to quantity with different dimension. For example, it is meaningless to say that to add like a 1 kilometer with 1 kilogram. What does it mean? 1 kilometer plus 1 kilogram. There's no meaning on that because we cannot add two quantity with different dimension. Okay, so that is the rule. It's something that makes sense, right? The third condition is what I already mentioned, that the quantity on both sides of an equation must have the same dimension. Must have the same dimension. Okay, so you can use these three conditions to check your result that it makes sense or is reasonable or not by looking at the dimension of your result. Let's see an example. This is very simple example. This is the very basic equation of motion, very basic equation of kinematic. We will study this equation in more detail in the next chapter, but now let's write it down like this. X is equal to x0 plus Vt plus half of the at square. This is a V0. X0 is the initial position of a particle. V0 is the initial velocity of the particle, and A is the acceleration of the particle. First, we must have that on the left, the dimension of X is the length must equal to the dimension of x0 times the dimension of v0 t, not times, sorry, plus the dimension of v0 3 plus the dimension of half of a t square. You can see that we do the addition on the line, so all terms on the line must have the same dimension. It means that x0, v0t, and half of at square must have the same dimension. So let's see. You can see that the dimension of x is the length, which is L. The dimension of x0 is the length too. The dimension of Vt is equal to the dimension of V0 times T. This is the, as we say, we can write down it as the algebraic multiplication of each dimension. And again we have that the dimension of half of the at square is equal to the dimension of the half times the dimension of a times the dimension of t square, which we can write it as the dimension of t times the dimension of t, okay, which is equal, the dimension of v0 is length over time, and the dimension of time is of course t, plus the dimension of half is 1, it's just a number, so we have that the dimension is 1, it's just a number, right, time the dimension of a, which is equal to L over t square, and the dimension of t times the dimension of t is t square. So you can see that the dimension of t and t here can be cancelled, the dimension t square and t square here can be cancelled, so you have this as the dimension of L plus L plus L. We never say that this is a dimension of 3L. There is no meaning, because this is the dimension of L and L and L, and this is L, the length. So we have that L is equal to L. That is, the dimension of both sides of the equation are 3, and this equation seems to be correct, as we know that it is correct. So this is an example of the dimensional analysis. Dimensional analysis. Now, once we have the dimension of the quantity, we next have to give them the unit. And of course we have the basic unit, the kilogram, the meter, the second, but sometimes we need to convert the unit to be appropriate for the quantity that we are interested. For example, it is not proper to give the resource, for example, your height in the unit of kilometer, okay, or it's not proper to give the time, I mean your age, for example, in terms of second. So we always have to do the conversion of unit. This is an example, some examples of the conversion. For example, you can convert the mile into kilometer, the meter into inch or into feet, and in the opposite direction from the feet to inch, or from the feet to meter, or from inch to meter. An interesting example is the last one, that is you have that 1 inch is equal to the 2.54 centimeter, and this is exactly, it means that this is the definition of the inch. Now the inch is defined in terms of the SI unit.